see you and good to have you back. This month's Berlin Machine Learning Group meetup. It's a great pleasure to introduce tonight's speaker, Simon Wiedemann of the Technical University Munich. Simon is a master's student of mathematics at the Technical University Munich, as I said. He's currently finishing his master thesis in the field of quantum reinforcement learning in collaboration with Siemens. He is interested in the theoretical as well as the practical aspects of data science, statistics, deep learning, and more recently, quantum computing. As a working student, Simon developed deep learning applications at a healthcare company as well as at a legal tech company. It's a very first tonight that we talk about quantum computing with applications in the context of machine learning. To be specific, the title of his talk is Quantum Neural Networks. Simon promised us to keep the number of formulas at a minimum. And with that, I would say I would give the mic to Simon and take it from here.
Thank you very much, Adrian, for the nice introduction and the kind words. You already said everything that is necessary regarding preparation, so I can go ahead, share my screen, and we can start the presentation. So screen sharing is running, I think. Adrian, is it working?
Yes, perfect.
Okay, great. So as Adrian already said, first of all, thank you very much for having me. It's an honor to have the possibility to speak in front of you and to tell you something about quantum computing and quantum neural networks. I hope to get some people interested in the field. So the title of today's talk is Quantum Neural Networks, but actually the title should have been, I realized, Introduction to Quantum Computing, and also some infos on quantum neural networks, because I wanted to keep the talk as self-contained as possible, and therefore I added a very lengthy introduction to quantum computing. I figured it would be good since, it's probably most of you are interested in it, but maybe don't have such a strong background in it. And it's always good to start from scratch. Sometimes, people who are experts in quantum computing already can skip the first part, but then let's get ahead and start with the introduction to quantum computing. So first of all, what is quantum computing and why should we care? So I took this definition of quantum computing from a book on quantum computing by Nissen and Zhuang. It's a very great textbook if you want to get started on the subject. Later you have a slide with the bibliography, then you can see which books are used. But this is a very good book to get you started. So quantum computing is the study of the information processing tasks that can be accomplished using quantum mechanical systems. So basically, we're using quantum mechanical systems or anything that behaves quantum mechanically, so to say, in order to do computation, right? So we replace our ordinary computer with a quantum computer. And why should we care about this? It's because quantum computers, they can do certain things much more efficiently than classical computers could. Okay, so there are two very famous algorithms. The first one is Peter Shor's algorithm for integer factorization, which was discovered in 1994 by Peter Shor, and it's an algorithm that's polynomial in time that factors that you can use to factor an integer into its prime factors, right? So mathematics tells you if you have a positive integer, then you can write that integer as a product of prime numbers, and finding these prime numbers is super difficult. So there is no known classical algorithm that can do this efficiently. For the experts, that can do it. So there is no known classical algorithm that can do it in time faster than exponentially, basically faster than exponential time. And Peter Shor found this quantum algorithm that can do it in polynomial time, which is a massive speed up. So once quantum computers become available large scale, at the moment they are not, yeah. So everyone's trying to get a big quantum computer that works well. So once quantum computers are available like on a large scale, then the famous RSA encryption algorithm that relies on this integer factorization has to be revised, right? Yeah, but don't worry, there are other quantum encryption. There are other encryption algorithms that are based on quantum computing that are probably safe. So it's got you covered. Yeah, so this is one famous algorithm, and another famous algorithm was discovered in 1996, which happens to be the year of my birth. Was by Lev Grover, and it's a search algorithm. So it's an algorithm that can search a database for a certain element, and it can do it quadratically faster than any classical algorithm can. So there's a mathematical proof that says, okay, under certain circumstances, there can be no classical algorithm that is as fast as Grover's search algorithm. So these are two very famous, super cool quantum algorithms. And these drew, especially Shor's algorithm, drew a lot of attention to the field, and everyone's trying to come up with super fast quantum algorithms to solve their problems. Yeah. So this is why we should care. Yeah. So in the talk, I'm focusing mainly on the algorithmic, on quantum algorithms and stuff. So no hardware talk because I'm not an expert in that. Yeah, but I mean, all you should know is that at the moment there are no like reliable realizations of large quantum computers. So everything we're talking about today is a bit in the future, but yeah, we should still look into it. So let's start with the actual introduction to quantum computing. So many of you, most of you have probably already heard the term qubit. Qubit means quantum bit. So, and the qubit is the quantum version of a classical bit. So bit is a unit, right? It's the basic unit of classical information. And a bit is a physical thing that can be in two states, and these two states are typically labeled 0 and 1. Okay, and a qubit is the basic unit of quantum information, and a qubit is realized via something that behaves quantum mechanically. I won't go into detail here on how a qubit is actually realized, but we're going to focus on the theoretical representation of a qubit. So a bit you would describe as an element of a set, right? One bit is, so the value of one bit is in a set, and that set contains elements 0 and 1. And a qubit is a complex vector, actually, okay? A qubit is a superposition of two basis vectors. So you have these two states, 0 and 1, and these are related to the classical bit states. Okay, so think of this 0 is a classical bit in state 0, and this 1 is a classical bit in state 1. And then a qubit is a linear combination of the 0 state and the 1 state. And this 0 here with this weird bracket thing, so this notation is called the Bra-Ket notation, and was invented by Dirac. Just for quantum mechanics. So this is the ket zeros. This is the ket 0 state, and this ket 0, which corresponds to the bit value 0, so to say, we represent as the first basis vector of a two-dimensional vector space. And this one basis vector we identify with the second basis vector. Okay, this is why these two elements here, the 0 and 1. They are called the computational basis because they form a basis of the so-called state space of a qubit. And the state space of a qubit is the vector space C2. So this is a tuple of complex numbers. Alpha and beta are complex, and they have to satisfy this normalization condition. Okay, so that means the modulus of alpha squared plus the modulus of beta squared is 1. And that basically means that the Euclidean norm of this psi vector is 1. Okay, I will tell you in a second why this is an important relation that alpha and beta have to satisfy. But for now, it's just important you know that they satisfy this relation, and that a qubit is a qubit. You can think of a qubit as an element in a vector space, and that element has to satisfy a certain norm relation. Okay, and this is a first example of a qubit. It's a very famous one qubit state. It's called the plus state. And here you see here these complex coefficients are both 1 over square root of 2. So alpha is 1 over square root of 2, and beta is 1 over square root of 2 as well. And they are both real. And yeah, so you see this is just a vector in this two-dimensional state space. Okay, so this is one qubit. Now let's talk about alpha and beta. These guys are called amplitudes in the language of quantum computing. And they cannot be observed directly. I will tell you in a second what this means. But they are related to probabilities, okay? And here comes something that probably most of you have heard about. It's the superposition principle, and it's a probabilistic interpretation. It's relation to probabilities. Now, this is a very hot topic. It's a topic that's controversially debated still to this day by physicists. I mean, not very controversially anymore probably, but you know, Einstein and Bell and, you know, Dirac, and they all argued about it. And yeah, it's a very difficult thing, this superposition principle, but let me try to explain you a bit what it means, okay? So, as I said, this qubit, this ket psi qubit, is a vector in a two-dimensional complex vector space, and it has these two amplitudes. And these amplitudes, so the moduli squared of these amplitudes, they correspond to probabilities. And what probabilities are they? So a qubit, I told you these alpha and beta, you cannot observe them directly, okay? So you cannot know with certainty in what state the qubit is. In order to do that, you have to do a so-called measurement. We call this a quantum measurement, okay? So you have the qubit, it's in a superposition, but if you want to know something about it, you have to do a measurement. And that measurement is stochastic. What do I mean by that? So if you measure a qubit, you can obtain two values, either 0 or 1. And you obtain them with the probability. So you obtain 0 with probability modulus of alpha squared, and you obtain 1 with the probability modulus of beta squared. Okay? So in some sense, these amplitudes are the probabilities that I measure 0 or that I measure 1. Okay? So that's the way to think about these amplitudes. Note that this does not mean the qubit is in state 0 or in state 1 with certain probabilities. It's the probability that we measure the qubit in state 0 or we measure the qubit in state 1. That's a huge, huge difference. The qubit is in no definite state until, I mean, it is in some state, in a superposition state, but it is in no state 0 or 1 with certainty until we decide to measure it, okay? It's a common thing that's a bit confusing about superposition. Okay, so and what happens if we measure? Okay, I told you we can measure the qubit and then we can observe 0 or 1. So if we observe 0, the qubit, which was previously in this superposition, collapses to the 0 state. And if we measure 1, the qubit collapses to the ket 1 state. Okay, so that means if we measure the qubit, we change the qubit, okay? And that's a fundamental difficulty of quantum computing. So you have this qubit, and it's in a superposition state, and you want to do something with the qubit, or you want to know something about the qubit. But as soon as you decide to measure it, you change the qubit, okay? And this makes everything pretty tricky, okay? So let's have a look at a concrete example, so to say. So, for example, this plus state, if we measure this, right? I told you this alpha, the modulus of alpha squared is the probability that we measure 0, modulus of beta squared is the probability that we measure 1. So if we have a qubit that's in this plus state, it means if we measure it, we measure 0 with probability 1/2, right? 1 over square root of 2 squared is 1/2, and 1 over and with probability 1/2 we measure 1. So measuring this qubit can be thought of tossing a fair coin, okay? So if you toss a coin, it can land heads up or tails up. And if you measure this qubit in this state, you can measure 0 or 1, both with probability 1/2. Okay. And there's one thing I want to point out. All of this now becomes statistical, right? So because the qubit is in the superposition state, and if you want to learn something about the qubit, you will measure it multiple times. Sometimes you receive 0, sometimes you receive 1. Then you can kind of estimate some empirical distribution, or you can estimate an expected value. So, you have to typically repeat quantum mechanical experiments like a number of times, and you will get different outcomes because of the inherently probabilistic nature of all of that. Okay, so the content of these 2 slides was already a lot, and probably I didn't explain it very understandably because it's super difficult, and that's why I prepared like an example for you. So this link redirects us to the IBM Quantum Circuit Composer, and here you can play around with qubits, right? So this is a quantum circuit, what you see here, and this here where my cursor hovers is a qubit, and the qubit is initialized in the 0 state. Okay, so if I remove this gate, you see that the probability that this qubit is in state 0 is 100%. Okay, probability is 100% that it's in state 0. And that means if we measure it, so this is the measurement symbol, we will measure it in state 0 with probability 1. Okay, so here we can change the seed. So this means we do another round of the experiment. No matter how we change the seed, that means no matter how often we repeat the experiment, it's always in state 0. Okay, but now if we add a gate, namely this rotation Y gate, I will tell you later what this means, okay? I will tell you what this means later. For now, it's just important the state of this qubit, okay? Now I changed the state of the qubit, and now I can zoom in a bit, yeah. Okay, yeah. Thank you very much, Abhishek. Yeah, so now what changed is the measurement probabilities, right? So now if we measure this qubit, it's in state 0 with probability 0.75, and it's in state 1 with probability 0.25, okay? So now it is in the superposition, and once we measure the qubit with this measurement, this superposition will collapse, okay? Watch closely. Bam, okay? Now it's in state 1, okay? With probability 25%, it was in state 1. And now we can repeat this experiment. Now we measured it in state 0. Okay? And we can repeat this experiment multiple times. Sometimes we will measure it in state 0. Sometimes we will measure it in state 1. Okay? But if I remove the measurement, it's in the superposition state. Okay? But the superposition state collapses as soon as I add the measurement. Yeah? You see? Okay. That was already that's already one important thing, that this measurement changes the qubit. Okay, there is another thing about qubits which I want to tell you about. So I told you a qubit is a vector in a 2-dimensional complex vector space. So you would kind of think it's something 4-dimensional, right? Because you have a real part and an imaginary part for each component. There are 2 components. So 2 real parts, 2 imaginary parts, something 4-dimensional. But with some mathematical derivation, you can actually show that you can represent a qubit as an element on the 3-dimensional unit sphere, okay? So the 3-dimensional unit sphere is the set of all points in real 3 dimensions that are normed such that the norm is 1, okay? And this condition that the norm of the vector is 1 corresponds to this normalization, right? The normalization that modulus alpha squared plus modulus beta squared is 1, okay? And they have to be 1 because probabilities sum up to 1, yeah? So this normalization corresponds to forcing the state of a qubit to be a vector on the 3-dimensional unit sphere, yeah? And on this unit sphere, it is called the Bloch sphere, according to its discoverer, Felix Bloch, I think, was his name. And here you can see the 2 basis states, so the 2 classical bit states 0 and 1 are at the north and at the south pole. And each qubit can be represented on the sphere, and each point on the sphere corresponds to a qubit. And it has to be on the sphere. So if the vector weren't on the sphere, it wouldn't be properly normalized, and then it wouldn't be a qubit anymore, okay? So now if I say, think of a qubit, you just think of a three-dimensional vector that has norm 1. Yeah, that's the most intuitive or the most accessible picture you can have of a qubit. And on this Bloch sphere, we can also see why the qubit is a generalization of the classical bit. So we can think of the classical bit as a qubit that can only have values 0 or 1. So this qubit is only at the North Pole or at the South Pole. And the qubit is in between the poles. So the qubit is a true generalization. Okay? And that's what makes quantum computing so cool, because it kind of encapsulates classical computing, and you can do more with it. So now let's talk about single qubit gates. When I showed you this quantum circuit, I already told you that I applied a gate. So what is a gate? So if you think about what your computer does, it doesn't just represent a bit, right? If you just represent a bit, then nothing happens. Your computer uses logical operators, and, or, NAND, NOR, stuff like that, in order to process data, okay? And the quantum mechanical analog of this is a quantum gate. And these quantum gates are represented by matrices. I said a qubit is a vector, is a two-dimensional complex vector. So we can apply a matrix to the two-dimensional vector and get another vector, okay? But I also said this vector has to be normalized. And that's why this, not every matrix is a quantum gate, but the matrix has to be unitary. And unitarity is equivalent, at least in finite dimensions, in infinite, I don't know, to norm preservation, okay? So this norm preservation means that if you apply this matrix to a qubit that has norm, it will preserve its norm, okay? So if I have a qubit and I apply a gate to it, so this matrix, I will get another vector, and that vector also has to have norm 1, because otherwise it's not a qubit anymore, okay? So, and these restrictions come from the laws of quantum mechanics. Okay, so let's illustrate this with an example. So there's this very famous quantum gate. It's called the Hadamard gate. Hadamard gate, as all quantum gates, is linear, and a linear operation is uniquely defined by defining its action on the basis vectors. Okay, basis vectors of the two-dimensional one qubit state space are 0 and 1. Okay, so if I define the Hadamard gate on the cat 0 state and on the cat 1 state, I defined it completely. Right? That's basically equivalent to writing down its matrix. So what this Hadamard gate does is it turns the classical 0 state into this plus state that you already know. So into this coin state, I would like to call it. So you can think about the Hadamard gate. So if you have a coin that is heads up, let's say 0 is heads, what the Hadamard gate does is it tosses the coin into the air and starts rotating it, and will rotate until you decide to measure that state. Yeah. And the Hadamard gate on the 1 state kind of does the same thing. So you have this minus here. So you have the coefficients, the amplitudes, 1 over square root of 2 and minus 1 over square root of 2. But if you square negative 1 over square root of 2, you will still get 1/2. So this minus kind of doesn't really matter for this illustration. It does matter for some algorithms, but here it doesn't, okay? So think of the Hadamard gate as you have a coin and you start tossing your coin. Yeah. So that's the first example of a 1 qubit gate. And we can again, we can go, okay, let's visualize it on the Bloch sphere. Okay, so we start in a qubit that's in the 0 state. So this red arrow here points to the North Pole, and that means the qubit is in state 0. And then we apply the Hadamard gate, and you see it rotates this red arrow here onto the x-axis, and now it's in the superposition state. And now we decide to measure the qubit. With probability 1/2, it snaps back to the North Pole. And with probability 1/2, it snaps to the South Pole. So depending on where this vector lies in the sphere, so if it's in the upper hemisphere, the probability that you measure the North Pole is higher, okay? So depending on where it lies in the sphere, this influences the probability with which you measure 0 or 1, okay? So this is the action of the Hadamard gate on the Bloch sphere. Let's recap. You have a qubit that's in a state with certainty, it's in state 0. Then you kind of toss the coin, it's spinning. Now the coin is spinning if the arrow is here on the x-axis. And then if you kind of grab the coin out of the air, if you measure it, then you will measure heads or tails with probability 1/2. And that's how you should think about quantum gates. A quantum gate, and it turns out, in fact, that any quantum gate is a rotation or a reflection of a vector here on this Bloch sphere. And let's have a look at what this looks like in our nice IBM quantum thing here. So again, we start with one qubit that's in the 0 state. And I have to zoom out a bit, unfortunately, because it restricts the screen space here a bit. And then let's look at the probabilities later. Okay, we again start with a qubit that's in the 0 state. And you see, again, it is 0 with probability 1. And now let's apply a Hadamard gate. Hadamard gate is here. Well, what happened? Now, if we decide to measure the qubit, we measure 0 with probability 0.5 and 1 with probability 0.5. Okay, so now the coin is spinning, and now we can measure, and we measure 1. Okay, so let's take another experiment. We measure 0. Measure 0 again, and 1, 0, 1, 0, 1. Okay, you see this now with probability 1, I measure 1. If I remove the measurement, then I do not destroy the superposition, and I'm still in this equal superposition. If I add the measurement, we have wave function collapse. Okay, and this is a quantum circuit with which we can play with the plus state. Good. So one qubit alone can't do much. So if you think of your computer and you would think, okay, I have a computer that can process 1 bit. Yeah, what can it do? It can do nothing. I mean, next to nothing. So nothing that's really difficult or that you couldn't do yourself. So we need more qubits. And we know that if I have 2 bits, I can describe 4 states. Okay? If I have 3 bits, I can describe 8 states. And if I have 4 bits, I can describe 16 states. If I have n bits, I can describe 2 to the n states. And same goes for qubits, actually. So if I have 1 qubit, I'm in a 2-dimensional vector space. If I have 2 qubits, I'm in a 4-dimensional vector space. If I have 3 qubits, I'm in an 8-dimensional vector space. And if I have n qubits, I'm in a 2 to the n-dimensional complex vector space. And the mathematical way to notate this, so you see I have 2 qubits, and qubits are two-dimensional vectors, and we multiply them with the so-called tensor product to get a 4-dimensional vector. Okay, this is not so important. I just wanted to show you because it shows you how you make a 4-dimensional array out of 2 2-dimensional arrays. And this exponential growth is why simulating a quantum computer is very hard, right? Up to now, what I basically told you is that quantum computing is linear algebra. And linear algebra we can do in Python, right? So I will just, import numpy as np, and then I will just, some qubits or some normalized vectors, I will just apply some matrices to them, who cares? But, for example, think of a system of 100 qubits. Then your matrix has dimension 2. Then your matrices that correspond to your qubit gates and operations, they have dimension 2 to the 100 squared. And even your state vectors have dimension 2 to the 100. And it's just ridiculous. So it's exponential growth in the number of qubits. That's why it's hard to simulate. Okay. And what I would like to note is I said the dimension of the state space of n qubits is 2 to the 2n. So you also have more basis vectors, right? So if you have one qubit, you have two basis vectors, ket 0 and 1. If you have two qubits, you have the state of 2 bits as basis vectors, basically, okay? And then the state of 2 qubits is a linear combination of these 4 basis states. And then there are also multiple qubit gates, okay? So a 1 qubit gate acts on 1 qubit, and an n qubit gate acts on n qubits, okay? So for example, there's the controlled NOT gate that acts on 2 qubits. Again, I define it for all the basis states, right? 2 qubits, they live in a 4-dimensional complex vector space. There are 4 basis vectors, and these are the 4 basis vectors. And what the controlled NOT gate does is, if the first qubit is 0, it does nothing. But if the first qubit is 1, it flips the second qubit, okay? So here, the first qubit is 1, and the second qubit is 0, and that's why the C NOT gate flips the state of the second qubit, okay? So that's kind of a quantum if statement, if you wish. And of course, also 2 qubit gates have a matrix representation. Not so important here, this matrix representation, just wanted to show you that it is indeed a 4x4 matrix. And now I can tell you something that's very special about quantum computing. I needed to tell you about 2 qubit states because it only becomes relevant for 2 or more qubits. And this is called entanglement. And we can think about entanglement the following way. I told you that measuring a qubit corresponds to a random variable. So if you have a 2 qubit system and you measure it, it kind of corresponds to 2 random variables. And these 2 random variables can be dependent. And this dependency is what quantum people call entanglement. So let's have a look at how it works, okay? So suppose you have 2 experimental quantum physicists who are called Alice and Bob, and they live far away from each other. And some time ago, they met and created a qubit pair that is in a certain state. And the qubit pair is in the so-called Bell state. It's a very famous state. That's why it has a name. It's the so-called Bell state. Okay, so let's have a look at the Bell state. The Bell state is kind of similar to the plus state, but here you have 2 qubits, right? So this is Alice's qubit with the subscript A, and this is Bob's qubit with the subscript B. So if you were to measure these 2 qubits, you would measure 0, 0 with probability 1/2, and you would measure 1, 1 with probability 1/2 as well. Okay, that's what happens if you measure the 2 qubits. So that's kind of it's the same thing as the plus state. Not quite, because here there are 2 qubits, right? And what Alice can do, Alice can measure her qubit and leave Bob's qubit. She can apply gates on her qubit as well, and she can also measure only her qubit. So suppose Alex is in one place of the Milky Way and has her qubit, and Bob is on the other side of the Milky Way, and he has his qubit as well. So Alice only has access to her qubit. And what does she do? She says, I have this qubit, let's measure it. I want to know what I want to measure my qubit. Okay, so she measures her qubit. And she will measure 0 with probability 1/2, and she will measure 1 with probability 1/2 as well. But what happened? If Alice measures 0, this state here collapses to 0, 0, okay? Why does it collapse to 0, 0? Because there are only 2 possible configurations, 0, 0 and 1, 1. And if we know that Alice's qubit is 0 because she measured and she changed it, then it must collapse to this tuple here. But that means Alice's measurement changed Bob's qubit. Okay, let that sink in. Alice is here on Earth and Bob is on Mars or Pluto or I don't know where. And Alice measured her qubit and she changed Bob's qubit. And that's why Einstein, I think it was Einstein, I'm not sure. Somebody, so it's a very famous name, called this spukhafte Fernwirkung. In English, spooky action at a distance. And that's why many people also mistrust quantum physics a bit, because it's super strange, right? And because this wave function collapse is instantaneous. So things happen faster than light, but then actually they don't. Super difficult. I don't know much about it, but so this entanglement is a very important property, and this entanglement kind of also lies at the heart of most quantum speedups for quantum algorithms. So entanglement, super, super important. And entanglement basically means that measuring these two qubits is a dependent random variable, right? Dependence means if I know something about one variable, I also know something about the other random variable. And if I know something about Alice's qubit, I know something about Bob's qubit, okay? And two bits, so just the state alone of two classical bits is never dependent. I mean, okay, I mean, they might be dependent if they're connected to some gates, but this is just the state of two qubits. Okay, maybe the state of two bits is dependent, sorry, might be dependent. But here you see that these qubits, this is why you call them entangled. So you have to consider them jointly. You can't consider them individually. And changing one also affects the other one. Okay? And this is also at the heart of the very famous quantum teleportation. I will not tell you about quantum teleportation. Some people have maybe heard it. It's about quantum information exchange. And this entanglement lies at the very heart of this mechanism. So let's go back to IBM and have a look at this weird entanglement that Simon just told us about, okay? So let's start again with one qubit, and let me add another qubit, okay? So here you see one qubit, state 0, 1, with state 0 with probability 100%. Now I add another qubit, whoosh, I get, okay, so this is a bug actually here. I get 4 possible states that can occur just by adding another qubit, right? See? Okay. Then what I will do is I first apply a Hadamard gate to the first qubit, and then the C0 gate. And now we see this is the state I just described to you. If I measure this state, I get 0, 0 with probability 50%, and 1, 1 with probability 50%. And now let's say this is Alice. No, Qiskit counts the other way around. So let's say this is Alice. Let's measure Alice's qubit. And we have the wave function collapse, okay? Alice measured her qubit as 1, and Bob's qubit changed to 1 as well. So we can run the experiment another time. Yeah, okay, now Alice measured 0, and Bob's qubit turned to 0. Okay? Same goes if we measure Bob's qubit, by the way. Doesn't matter. Okay, so if we remove it, it's in the superposition. You know, and both people, and both Alice and Bob, they could observe 0 or 1 with probability 50%. But once one of them decides to measure, they change the qubit of the other one. Okay, that's very important. That's entanglement. Okay, so and now one last thing about quantum gates. I already told you you can think of quantum gates as rotations on this block sphere, and it turns out that there are gates that are so-called rotation gates. So the block sphere is the sphere, and you can rotate points on the sphere around the coordinate axis, and these rotations with certain angles, right? So the rotation Z gate rotates the qubit around the Z axis, alpha degrees, and the same goes for Ry and Rx. And these are the so-called single qubit rotations. And it turns out that these single qubit rotations, if you build any combination of them, you can build any single qubit gate. And then if you add a controlled NOT gate, you can use these 3 gates to obtain any quantum gate you like on any number of qubits. It's basically rotations. So again, this one with this, I just want to encourage you to think about qubit manipulations as rotations of unit vectors in 3 dimensions. Okay, I just rotate them somehow. And if you have multiple qubits, they are in a hyperblock sphere, and then you rotate them on the hyperblock sphere. Okay, nothing special, just super high dimensional geometry. So it's special enough. And these are universal quantum gates, right? So your classical computer has universal gates, which is NAND and NOR, and universal quantum gates are these rotations and the C0, which creates entanglement. So this constitutes, this finishes the introduction to quantum computing part. I agreed with Abhishek and Adrian that if there are already enough questions for a quick intermediate Q&A session, I would allow questions now. Adrian, are there questions?
Yes, there's a question. Actually, you answered it, but I'm pretty sure you like to rephrase your what you just said in another way. The question goes like follows: there are only a handful of named quantum gates. Does it mean that other unitary gates are not considered useful in quantum computing?
Oh, no, they are considered useful, but some gates are just special for historical reasons. And it also depends a bit on, so I already told you can build all the single qubit gates out of these gates. So theoretically, we would only need these 4 gates in the first place. But then there also comes a bit of hardware into play. Depending on how you realize your qubits, your quantum computer, certain gates are easier to implement on certain physical systems than others. And that's why, also it depends on the hardware. There are certain gates they call native gates. And that's why there is actually a variety of gates. But all of them can be built out of those gates. Okay, but this is all in theory, right? We mathematicians, we like to live in the theoretical world where there's no problems with implementation and realization. But yeah, it's not always that easy. I hope that answered the question.
Yes, definitely. Let's move on to the second part of your talk.
Okay, now it gets a bit more involved. Quantum neural networks. So let's talk about the basic idea of quantum neural networks. Okay, so what is a neural network? A neural network is a function that is parameterized. Okay, a function that consists of weight matrices, so of linear layers and nonlinear activation functions. So you if you have an L layer neural network, you have L weight matrices and you have L nonlinear activation functions, and then you apply them sequentially. And then you have a parameterized function, right? And the parameterization lies in these weights here, okay? And I already told you that a quantum circuit is just a collection of gates. And gates are, also, they are just matrices. They are just linear operations. So the idea of quantum neural networks is you replace these classical parameterized blocks by parameterized quantum gates. And parameterized quantum gates, for example, are rotation X, Y, and Z gates because they have a certain parameter, right? So the parameter is the angle, the rotation angle around a certain axis. Okay, so for example, this is, for example, a quantum neural network, and it already looks a bit like a classical neural network. So what happens here is you have to input. Let's start here, okay? But there are certain problems, right? So the neural network, what you do is you give a vector to the neural network, and the neural network operates on the vector and then outputs something, a probability distribution or 0 or 1, stuff like that. But already giving the vector to a quantum circuit is difficult because I told you that the state of qubits is basically a vector in a high-dimensional space. So you would think, okay, I just prepare this vector as a quantum state and give it to the network. But that's typically expensive or super difficult. So preparing this vector as an n-tuple is super difficult in most cases. So that's why we can't do it. How can we input the data? And then also another problem is the quantum circuit outputs a quantum state, right? So a quantum circuit, if you don't measure it, only has quantum information. So we also have to think a bit about how can we get classical information from the quantum state, and that is done via measurements. And there you already hear, okay, measurements, we will have to repeat them multiple times again, because measurements are realizations of random variables. And one sample of a random variable, what's that? It's nothing basically, unless it's a super stupid random variable. Okay, so those are two problems. So let's look at how they are solved. So in order to input the data, what you do is if you have a vector, here you have a 4-dimensional vector, x1 to x4, you apply certain rotation gates on some basis states, okay? So you have 0, 0, 0 is always the initialization of any quantum circuit. Then you apply some Hadamard gates to bring some superposition into the game, and then you encode your data by rotation angles, right? So if you kind of, that's what happens. So you write your data point as rotation angles, and then you rotate, and then you kind of input your data, and then what you do is you apply parameterized blocks, okay? And here you see we apply rotation gates, because rotation gates are universal. They can realize all unitary transformations together with the C0. So we kind of come up with an architecture. So in a classical neural network, you come up with an architecture with matrices and their shapes. And here the architecture is which rotation gates do we use, where do we place them, and then also we use entanglement, because entanglement, I told you, is a fundamental resource of quantum computing. And note that this data encoding block encodes the data point, so it's not trainable. So these x1, x2, this only depends on your data. And what you train are these parameters, the rotation angles of the rotation gates. Okay, so the quantum circuit works as follows. You have a data point, x1 to x4. You calculate these values. You input them to the rotation gates. Then you apply these rotation gates and measure the outcome. And you measure it multiple times and estimate the expectation, okay? So this measurement will give you one value, this measurement will give you one value, this and this. And then you can average them, okay? And for example, let's say you have a 4-class classification problem. Then you say, okay, if I measure this, it will be a value between 0 and 1. This is the probability, or this is the confidence. No. So you will measure 4 values that are between 0 and 1, and then you do softmax on them, and then you get a probability distribution, okay? So this is kind of the output layer, these measurements, these are the output layer. And if you repeat, you can repeat this multiple times, and then, you will get the expectation value here. That's always a bit the caveat, you have to repeat it multiple times. But the path of data is you encode it as rotation angles, you apply the parameterized rotations, you measure, you do that multiple times, then you do post-processing and get your output. So for example, if we want to do a 4-class classification problem, in 4 dimensions, then I encode the data point here in this, via these rotation gates, and I will obtain these 4 numbers. I will repeat it. So for one data point, I will repeatedly do this, then apply softmax, and then get my class probabilities. So this is how you would solve a classification task with a quantum neural network. Okay, but the important thing about a neural network is, of course, always how do we train the neural network? And we train it with gradient descent. And we train the quantum neural network in the following way. So here, this is an abstraction of what I've just showed you, okay? So here, some data point X enters the neural network. The neural network is here abbreviated by U. So this X here is the output of the state preparation of these rotation angles, basically. So we kind of encode the data, then we apply our parameterized gates, and then we measure it. And then we have our outputs depending on these measurements. And then we can also calculate a loss function. And then based on this loss function, we update the parameters. So that's the classical learning routine of classical neural networks as well, right? And how do we do it for classical neural networks? We use gradient-based optimization, ADAM, for example. And for that, we have the backpropagation. The thing is, I already told you, this is kind of also a neural network, right? It's the repeated application of matrices. So we could also use backpropagation here. But I told you that the size of these vectors blows up incredibly with the number of qubits you add. So you can't do backpropagation efficiently. And there is another way which you can use to calculate the gradients for these weights. I will not show you how to do it, But these gradients, again, have to be sampled. So these gradients are written as the expectation values of certain random variables. So in order to calculate the gradient, you also have to repeatedly run the circuit and estimate the gradients. And then based on that, you can update the parameters. Okay, so the model inference, that means sending a data point through the quantum neural network, is estimating an expectation value. And training is also estimating an expectation value. So let's have a look at the comparison between classical and quantum neural networks, okay? So quantum neural networks don't have an activation function because activation functions are nonlinear. And I told you in quantum computing, you can only apply linear gates, okay? But you introduce a certain nonlinearity through this tensor product. This is a bit more for the experts amongst you. There is nonlinearity in the quantum neural network, but it doesn't come through a predefined nonlinear function. It's introduced via the tensor product. If you wish, I can tell you a bit about it, but this would be way too formula heavy. Okay, so there are no activation functions, but you have nonlinearity. Okay, in the classical neural network, you can just directly input your data vectors, and here you need an encoding block, right? So this is the encoding block. Here we just apply the matrices and the nonlinear activations and can just use the output directly. And here, in order to get the output, we have to sample. We have to estimate something via sampling. Here we can have gradients via backpropagation, and here we have gradients via the so-called parameter shift rule. This is how you calculate the gradients. And again, we have to sample for that. And if you look at the table, you would say, wow, quantum neural networks are absolutely shitty because they are so much more difficult to handle than classical neural networks. And they are much more difficult to handle. So why should we care? Why should we bother? So if you think about it, classical quantum computers are proven to be more efficient and to be able to realize certain operations much more efficiently than our classical computer, despite all these sampling and estimation problems. And if you think what a neural network, but it's super difficult to write quantum algorithms. So I tried to write some quantum algorithm for a master's thesis. It's super difficult. Okay, so Peter Shor is a genius. Grover is a genius. They are all geniuses, the guys that write these algorithms. But it's also super difficult to write an algorithm for image classification, right? That's why neural networks were invented, right? Let the computer learn how to write the algorithm. And so we want super fast and efficient quantum algorithms, but we don't know how to write them because it's super difficult how to write them. So let the quantum computer learn how to do it, okay? That's the spirit. That's why we want quantum neural networks. That's why we want the variational approach. Let the quantum computer figure out how to do the super complicated math. Then also people who are just, averagely intelligent, just like I am, can also, use quantum computers to solve their super difficult problems. And I don't have to be as smart as Peter Shor or Lev Grover, I mean, I don't, then it was just a joke, right? Then it just makes it more easier. You don't have to cook up a super complicated quantum algorithm. So let the quantum computer learn the algorithm. That's why we want it, okay? That's why we want to bother. And there's also theoretical and empirical evidence, which I will show you in the next slide, that these quantum neural networks perform better. I hesitate to say they are better than classical neural networks, but there is evidence that they have some advantages. And so there is this paper, ASZ Plus, I don't know what it's called, but you will see later. And there they kind of ask themselves really this question: why should we bother with quantum neural networks? Are they better or worse? And what they did is they took a very famous data set. First of all, they did super complicated formula work. Then they took a data set, which you all know. It's called the IRIS data set, right? It's a it's a 4-class classification problem. I think a 4-class classification problem in 4 dimensions, and it's about classifying flowers. And what they did is they only took 2 classes of the IRIS data set and solved this classification task using quantum neural networks. and using a classical neural network, both of comparable size. And because they implemented this on a real quantum computer, and there aren't, you don't have access to a big multi-qubit quantum computer, they could only use models that have 8 trainable parameters, okay? So they couldn't, so if you see this loss converges to 0.2, this is very bad in practice. But, they used a very small model. That also has to do with the fact that qubits are very noisy, and it's super difficult to do proper computations with them on current machines. So they kind of spun up a small, it was actually this very architecture they used to solve binary classification on Iris. And then they also used a classical neural network with 8 trainable parameters, and they trained it for 100 epochs. And you can see, here you can see 4 curves. The red one is the classical neural network. The first one is called easy quantum model. It's called easy because this is a quantum model that's easy to simulate on a classical computer. And you see it behaves similarly to the classical neural network, a bit worse, actually. It's reasonable that it behaves a bit worse because quantum computing is much more restricted than classical computing. And then they used another quantum neural network, one for which they know, which is difficult to simulate classically, right? I already told you it's difficult to simulate quantum computing. That's why quantum computing is used, or that's why it's interesting. If it were easy, then we would just simulate it classically. So they kind of used a quantum architecture for which they know is difficult to simulate classically, and that learned much faster and much, much better than the easy and the classical neural network. And these are on simulators, and this black curve, IBM Q Montreal backend, is this difficult quantum neural network on actual quantum hardware. They trained it with all the sampling caveats and all these problems, and it was even better than the theoretical result. Okay, and I think this is a super nice, super incredible result, right? This is only the training loss value. So in their paper, they came up with theoretical arguments for why quantum neural networks should be easier to train. So they, depending on how you encode the data, they have less problems with vanishing gradients, right? And if you have less vanishing gradients, you can train more easily. You can train faster, okay? And what's super interesting is that the structure of these data encoding blocks plays a central role in the expressibility of these quantum neural networks, right? So expressibility kind of is the set of functions you can describe with your network, and this depends super, super strongly on how you encode this data. So it's funny, because at first I thought, okay, shit, you have to use this weird encoding block, then you can't really express nice functions. But this is actually the key, kind of, seems to be the key for some of the quantum advantages. So there is, forward. So there's also this other paper which investigated that, the influence of this data encoding strategy in great detail, and they showed that variational quantum circuits correspond to Fourier series, and that the frequency spectra of the Fourier series, they correspond to the data encoding strategy. So this is there is this theoretical work that suggests that they have less problems with vanishing gradients and also have a higher model capacity. So with fewer parameters, you can express more complex decision boundaries. And that's also reflected here, right? Not only does the model converge faster, it also performs better because it's more expressible with these 8 parameters. And already on real hardware. And that's why quantum neural networks are interesting, and that's why they are already interesting for the near term. Because quantum computing, there's this thing called NISQ applications, because quantum computers are super small at the moment, super unstable. So people are searching for algorithms that they can run on near-term quantum devices, and that these variational quantum circuits, these quantum neural networks, they are candidates for such applications. And we see here empirical evidence that we can really have benefits. That's the end of the talk. I would like to thank you very much for your attention. I would now happily receive questions. Please, please, please do not hesitate to ask any question. I know this field is super complicated. The introduction I gave you, actually, there would be multiple lectures in an introduction to quantum computing course. My professor talked like 3 hours or maybe even 4.5 hours about the first few slides. So yeah, it's difficult. Please ask any question that comes to your mind, and don't be afraid if you didn't understand certain things about the quantum neural networks. I didn't go into detail properly because it would be a bit too much maybe.
Simon, first of all, thank you very much for your wonderful and very lively talk. Yeah, we have a couple of questions. The first one being, could you go back to slide number 19, it is, I guess, where you showed the architecture, this one, yes. And the question that pertains to this slide is, can the shown architecture approximate any function as most classical neural networks can?
Mm-hmm. I don't know if this architecture can approximate any functions, but it is still very early. So, if you think about back in the days, people were not so sure about what's the standard way of defining a neural network. There are proofs that certain architectures, I already said, they are related to Fourier series. People are investigating what architectures can express which classes, but I know a proof sketch that's actually, you can extend it, that you can express any polynomial with these variational quantum circuits. And if you kind of extend that proof a bit, if you can approximate any polynomial, you can approximate any continuous function, and then you again have your universality if you take it to the multivariate level. So yeah, I don't know if this architecture can, but there definitely are proofs that architectures can do it.
Could you explain exactly what X1 is here? So the question is X1 the X1 here in the up there? Yes.
Yeah.
Is it meant as an instance, or is it a feature value of an instance?
It's a feature value. So you have a 4-dimensional feature vector. Iris data set has 4 values, and X1 would be this first value. I think it's sepal with, I don't know.
Okay. Thanks. Then here's a question: how would the architecture change? That is, which gauge would you use to accommodate binary output while keeping 4 input qubits? I'm not sure if I understand the question, but hopefully you do.
Mm-hmm. You don't have to change the architecture, basically. You have to remove the last 2 measurements. Or you can also say, just sum these 2 up. Right? After you have these values, you're free to do with them whatever you want and let the algorithm figure out how to cope with the manipulation that you did. Yeah. So you can control the number of outputs is limited by the number of qubits you use. But mostly if you think about image classification, you throw in a 1000 pixel image, I don't know, and you have a small output. I mean, you can do post-processing here, but an easy answer would be just remove 2.
Cool. There's a question regarding reinforcement learning.
Yeah.
I think reinforcement learning was somewhat in the abstract, but did you talk about reinforcement learning, or is it not part of this architecture?
So successful reinforcement learning algorithms actually use neural networks. And there is work that replaces the classical neural networks with quantum neural networks. But that's kind of not really quantum reinforcement learning, right? It's just, changing your tool a bit. So I didn't talk about this other part, but there is, for example, in my work, we kind of think about how can we simulate the interaction of an agent and an environment on a quantum computer, and how can we use this, especially the superposition principle, in order to evaluate the agent, for example. But this is a bit different. I didn't really talk about reinforcement learning.
Okay. Could you? I mean, there's a question. What is the archive number of this last paper that you mentioned?
Yeah. So
could you? I mean, it would be best if somehow you could share your presentation somewhere, so everybody would have access to it.
Yeah, I can share it, and then here you have the references.
And the next question is it possible to use the architecture for regression problems?
Yeah, it's also possible, because this expectation value is a number between 0 and 1, and you can also use standard regression things here. So mostly you don't use these numbers directly, you apply some post-processing. And yeah, I also already used it. It works just fine.
My final question is the following. So it's probability we are talking about.
Yeah.
My question is, and you said you have to repeat experiments to get an estimate for the stuff that you want to measure for the distribution.
Yeah.
But how often do you have to? Do you know, is there a rule that says you have to do like so many iterations of the experiment to get? How do you know when you are done actually? I mean, I do one experiment. I get in the simplest case, I get 1 or 0.
Yeah.
But how do I now? When do I know that I know that is like 50% or 25%? Is there a rule for that?
So that question is kind of unrelated to the quantum thing, because it's a classical statistics question. So the question kind of boils down to if you have a set of random variables, or if you have a random variable and you want to estimate the expectation, because mostly you want to estimate the expectation, you don't want the whole distribution. If you want to estimate the expectations, how many samples do I need? And that depends typically on the variance of the random variable. In practice, what you could do is you could use your empirical mean, and just see when it stops changing. For your architecture, just add some values and try to estimate some expectation values to get a feeling for how many samples you need. But worst case, if you think about a flat distribution that extends forever, you have to measure like crazy.
Yeah. There is a question regarding quantum field theory, but I guess you don't want to take that one.
I don't. I'm not a quantum physicist. Sorry. Maybe you can answer, Adrian.
Actually, I don't know the answer. I don't know this paper. It looks so. Jared, very much. Thank you very much for that question. I will look into it. And then a final question is: do you think the QNN can be used in the future to break RSA cryptography algorithms?
I think we already have Shor's algorithm. So if you have a large enough quantum computer, you mean if it can be used in the near term to break the RSA, probably. I don't know.
In the future.
I don't know. I really don't know. Sorry.
Alrighty, that was the last question. There were already a couple of big thank yous from the audience. Thank you again, Simon, for your very wonderful and very lively talk. It's awesome. I hope you come back, maybe presenting your master thesis in the next session. We would welcome to. Thank you very much. To the audience, if you have a project done and you want to share it with the community, please let us know. We are desperately looking for speakers for our next session, which will be in a month from now, in August. So if you have a project, small or big, drop us a note. If you want to discuss a scientific paper that you just read, or you just want to share a new machine learning algorithm or model that you want to discuss, please drop us a note, and we are happy to stage you. Simon, again, thank you very much, and
Thanks for having me.
yes, hope to get you back sometime soon.